Hello everyone, I'm making a series of videos explaining the chapter on quantum computing for the beginners, and this video is the first video of this series. In this video, I'd like to explain the most basic concept of how to define a qubit in the chapter ion system. As we know, for a classical computer, for every bit, it can only be either 0 or 1. However, in a quantum computer, each qubit could be the superposition of 0 and 1. This feature can help it to calculate simultaneously, so that for some particular problems, a quantum computer can calculate much faster compared with a classical computer. But how can we really build a quantum computer? First of all, we need to define a qubit. We need to define 0 and 1 so that we can have superposition between 0 and 1. So there are many different kinds of systems to realize for the physical realizations, and we need some criteria for that qubit so that it can work as the calculation element for a quantum computer. So the Professor DiVincenzo put forward 5 criteria. Professor DiVincenzo put forward 5 criteria. The first is that we can define it has well-defined two-level system, which could be defined as 0 and 1. And this two-level system should be away from the environment. It should not be affected by the environment. For example, it cannot be leaked from 0, 1 to other states. And this is the first criterion. The second one is that it can do the initialization. It means that we can prepare the state to either 0 or 1. And we can prepare each qubit to the state 0 or 1 that we specify, so that it could be the initial state, and we can start the computation from that state. And the third criterion is that it can do universal gate operations. If for a computer, you need to be able to do any gate operation that you need, so that you can universally solve any problem, right? So technically, if you can do a universal single qubit gate and a controlled NOT gate in every 2 qubits, you can do a controlled NOT 2 qubit gate in every 2 qubits, and then you will be able to do universal gate operations. So this is the basic criterion. And the fourth type of criterion is that the decoherence time is much longer than the time to do a gate. What is decoherence? It means that the qubit could be affected by the outside environment or spontaneous emission, etc. And then it loses its coherence. It loses phase information, so that it can no longer work as a qubit. It loses information. So before the information is lost, you need to do enough gates that we want. So if this criterion is satisfied, we can do a lot of enough gates before the coherence is lost, so that we can do enough, so that we can use this to do quantum computing. And the fifth condition is we need to be able to do detection of the states. We do the calculation to get the result, and we need to use the detection to get the result outside. To detect at the end of the computing, we need to detect each qubit and let it to whether it is on 0 or 1. Yeah, we need to detect for a lot of times and get the average, so that we know the coefficients of the superposition coefficients of 0 and 1. Yep. And this is the 5 criteria. And for a trapped ion system, we can satisfy the 5 criteria above, and we will explain it. I will explain later. I will explain each process later, okay? And in this video, I mainly explain how to choose 0 and 1. And in the following videos, I will explain how to initialize and the ion to 0 or 1, how to do single qubit gate, and how to use different schemes to do 2 qubit gate. And I will also explain how to do detection process. We use the laser the state-dependent fluorescence to detect the ions. And then then we'll talk about what ions to choose from. You know, in element ion in the periodic table, we have so many elements, right? More than 100. And how can we choose the appropriate element? You know, as we all know, the atomic structure of the hydrogen is simple. Of the hydrogen atom is simple, right? It only has one electron and one positive charge. Yes, so the in the center of the atom, so that its energy structure is quite relatively simple. We typically, everybody has calculated this energy structure in the quantum mechanics class, and so we want our ion to have just one electron in the outer layer. So however, we don't want neutral atoms. We want ions. We want it to have a positive charge, so that we can use the electric field to confine it, and also use the Coulomb interaction to transfer information between different ions, and between, so that we can form some entanglement between different qubits. This is how we do it to communicate. So we hoped that the atom was originally has 2 ions in the outer layer, and then we use laser to ionize this atom, so that it has one positive charge, and it remains one electron in the outer layer. So what elements can satisfy this condition? The alkali earth elements, right? The alkali earth elements can satisfy this. For example, these alkali earth elements are quite very useful. And there are some other ions like ytterbium. Ytterbiums are very useful elements, a very useful ion. Okay, so these are the ions that we can choose from, and for each ion, it has many energy levels. How can we choose from the energy levels to form a Q-level system and to define 0 and 1? And there are several different kinds. There are several different choices. As we all know, for the hydrogen atom, for example, hydrogen atom, or just these ions are all hydrogen-like ions, right? So the energy structure is quite simple. It has n equals 0 or equals 1, 2, 3, and the angular momentum quantum number L equals 0, 1, n minus 1, right? It has this, and since it only has one electron, the S, the angular momentum of the electron is 1/2, and then so that its energy structure is quite simple. It's, you know, this n is the outer layer, the main quantum number of the outer layer. This is 2, 3, 4, 5, 6. Okay, and then whatever, but we just use n to denote this number, and this is ns. We have np and d, etc. And the n minus 1d, its energy is usually higher than ns and lower than np. Okay, it's just in between. And then we can define a qubit. How to choose 2 energy levels? The simplest way to choose it might be NS and NP. We may define this as 1 and this as 0. Is it okay? Maybe it's okay, but it's not good because, you know, NS and NP are electric dipole allowed transition, so that it's very strong. Even the spontaneous emission is very strong. For example, for ytterbium ion, the spontaneous emission rate is 20 million hertz, 20 megahertz. So its lifetime is just dozens of nanoseconds, even if simply due to spontaneous emission. It's very short, and for the gate operation, we can it's hard to have enough gate operations during this very short amount of time. So this criterion 4 is not satisfied. So it is not a good choice to choose S and P. A better choice is to choose this, S and D. We define this as 0 and this as 1. As we all know, for this, the delta L equals 2, which is not electrical dipole allowed. It's not allowed, so that the spontaneous emission is quite weak. For some particular ions, the lifetime of the D state could be seconds, even dozens of seconds, so that it's much longer. And during this time, if we do single qubit gate, the gate time could be typically 1 microsecond. So that and for 2 qubit gate, it might be tens of microseconds. So it's still possible to have billions of gate operations during this coherence time if you don't think of other decoherence factors. So this could be a good choice to form a qubit. Although this is not dipole allowed, we can use if our laser has a very short line width and a very strong laser power, we can still drive this transition so that have gate operations between 0 and 1. So this is a way to define qubit. We call this optical qubit. Because the energy gap between S and D are typically the energy gap is typically hundreds of gigahertz, just like it's quite near to the frequency of visible light. It's usually infrared laser. So that we call this optical qubits. It's just like optical transition. We use laser to do this transition. And there is another way to define qubits. You know, although it has a lifetime of several dozens of seconds, it's not long enough. If we want it to be longer, we have to choose another kind of qubit. Let's continue to do the atomic physics deductions. You know, this is we get L and S, and we know that if we calculate the L-S coupling, we can get J. Okay, that's for NS. NS is that is L equals 0 and S equals 1/2. So that J can only be 1/2. Okay, so this is 2, this is 1/2, and it only has one state. But as for P, it will be different. You know, as for P, L equals 1, S equals 1/2, and J equals 1/2 or 3/2. So it has two choices. Okay, it has two choices. This is 3/2, this is 1/2. Two states, two choices. As for D, it also has several different choices anyway. You know, as for D, L equals 2, S equals 1/2, and J equals 3/2 and 5/2. So that it has two states, okay? Two states. And -1, D 5/2, 3/2, okay? And we also consider the hyperfine states, okay? The angular momentum of the nuclear, so that it has IJ coupling. You know, for different ions, it has even different isotopes of the same element, it has different I, okay, different nuclear quantum number. It could be 0, 1/2, 3/2, etc. If I equals to 0, and then it has no ij coupling, and it has no, we cannot define this kind of qubit. It only has optical qubit. But if I is not 0, it's positive, it's, for example, 1/2, then we can have another kind of qubit. Okay, if I is 1/2, for example, here if I is 1/2, j also 1/2, then f could be either 0 or 1, right? So this could be further split to these two states, f equals 1 and f equals 0. And if we consider the Zeeman effect, this causes a split to 3 sub-levels, okay? 3 Zeeman levels. MF equals -1, 0, and +1, 3 levels. And for this, MF just equals to 0. So, and then we can define qubits here. We define this as 0 states, and this as 1. These are 2 states. And it nearly don't have any spontaneous emission from 1 to 0. It's nearly impossible, and the lifetime could be very long, even years. You know, it won't have spontaneous emission, but it will be affected by other things. Okay, the coherence time will be affected by maybe the collisions, or the noise of the laser, the noise of the microwave, etc. And the typical energy gap of these 2 states is gigahertz, much smaller than the optical qubit. So as we know, there are 3 states here. So you may ask, why do not use this or this? It's because that these 2 states could be, the energy of these 2 states could be affected by the magnetic field. And so could be affected by the magnetic field, which we don't want. So that if we, maybe because the magnetic field may be not stable, when the magnetic field has fluctuations, the energy levels of these 2 states will be changed. But these 2 states and energy is not sensitive. It's not first order sensitive to the magnetic field. So these 2 states we call clock states, because in the atomic clock people use these 2 states. Okay. So we successfully define these 2 states as qubits. This is for the isotopes of which has I equals 1/2. If I equals 3/2, it's harder. If it's a very more difficult situation, you understand? Because if I equals 2/2, j equals 1/2, and f equals 1 and 2. So for this state, it could be much more complicated, you know. F equals 2, F equals 1. It has 8 sub-levels. It's also okay for us to define this 2 as qubits, but as we can see in the followings, the state indigenization, the gate operation, and the detection are more difficult compared with this one. So maybe the best nuclear quantum number we want is 1/2. Yeah, it's not too simple to only have up to a qubit, or it's not too hard to have too many levels. This is very appropriate. This is something that we want, and then that is more suitable. But for this situation, we can also have advantages, like, for example, we can define qubits. Maybe for example, we define this as 2 exactions. This is a way to use this. Okay. So in this video, we talk about how to define qubit in a trapped ion system, which is the foundation to do the quantum computation. And we also have I also made a video in Chinese, and this video in English. The contents of these 2 videos are the same. So I use different languages because I want this video to be seen by both Chinese audience and the audience abroad. Okay, so it's nice. So yeah, and thank you very much. Bye bye.